So today we're going to actually finish our proof of the inverse function theorem, or the special case. And here I've put the screen that I started with last time, where these are all the things that we already have, and these are the things we still need to prove, although actually we now have proven this one, so we're finished with this one. So we're not going to use this phi sub y family of functions anymore. All you need to know for what we're doing today is the original assumptions. So f is a C1 function e to Rn, and you also need to know that we have this open set U, whose image is an open set, which we have called V, and the f restricted to U is a bijection. So you need to remember that. And you need to know that we have proven that the inverse of that bijection, the inverse of f restricted to U, is differentiable on V, and you need to know what we proved the derivative was. Then what we're going to do is prove that the derivative is a continuous function on V, and then we'll be done with the inverse function theorem. So let me just go remind you what the derivative was. So going back through our proof, it's right here. So the derivative of f restricted to U inverse, we showed, is the inverse of the derivative of f. So maybe a short way to describe this is our guess was that the derivative of the inverse is the inverse of the derivative. But to be able to state that a little bit more carefully, the derivative of the inverse of f restricted to U at y0 is the inverse of the derivative of f at the unique preimage for y0 that lives in U. So y0 might not have a unique preimage, but it does have a unique preimage that lives in U, since f restricted to U is a bijection. All right, so all the way through, this is all stuff that we did before. Now we are here. So I've added some text here, and our goal now is to prove that the derivative of f is continuous. So here's what we have shown. So I'm copying down kind of what we had from before. We have shown that the derivative of the inverse of f is the inverse of the derivative of f, evaluated where? At the unique preimage of y that lives in U. And this is for all y in V. And we have to prove that this is continuous, that this function of y is a continuous function of y. All right, so this is made out of a whole bunch of ingredients, right? So it would help to describe what is happening to y step by step. It's a composition of a bunch of functions. So let's start with y. Okay, starting from y, where does y go? So the first thing that happens to y is we apply the inverse of f restricted to U. So it goes to f restricted to U inverse of y. Okay, let's follow along in terms of sets and mappings, what's happening. Y came from the set V, and then after we apply the function f restricted to U inverse, which has domain V, we end up in U. Then what do? We apply f prime. So we map that to f prime of what we had previously, f restricted to U inverse of y. And then we take the inverse of that linear map. So this will be a linear map, and then we take the inverse. So we have this, and then we take the inverse. And okay, let's follow along in terms of sets and mappings. What happened from here to there? We applied the function f prime, which, well, I guess we applied f prime restricted to U, so that we have a function whose domain is U. Really, f prime has domain E, right? But I want to describe what's happening here overall as a composition of a bunch of individual ingredients. So here f prime restricted to U from U to L_Rn_Rn, the vector space of linear maps from Rn to Rn. That's what this is, right? It's a linear map from Rn to Rn. Then, what happens from here to there? Inversion. And we end up with another linear map from Rn to Rn. So here we end up with an invertible linear map from Rn to Rn, and here we end up with another, and from here to here we apply the inverse. So what's happening from here to there is inversion. Let me call that the inverse function that takes a linear map and takes its inverse. Okay, but that doesn't exactly make sense the way I've written it, because the inverse function is not defined on all linear maps, right? Not every linear map has an inverse. So let's fix that. Let me use this notation, following what Rudin uses, for the set of all invertible linear maps. Here, this is the set of all invertible linear maps. Maybe I'll just say that it's a subset of L_Rn_Rn. Consisting of all invertible linear maps. And inv is my name for the mapping from it to itself. The inverse of an invertible linear map is an invertible linear map, given by sending a linear map to its inverse. Okay, so now we have a nice description for what's happening to y when you apply the derivative of f restricted to u inverse. Is this composition of things is happening. So let me write that using composition notation. F restricted to u inverse prime, this function that I'm trying to show is continuous, works like this. It's inv composed with, I'm basically just reading this backwards because of how composition notation is kind of backwards, composed with f prime restricted to u, composed with f restricted to u inverse. So it's a composition of three functions. And if all three functions are continuous, then I can conclude that this function is continuous, and then I'll be done with the proof of the inverse function theorem. So are these continuous? Well, let's think. So f restricted to u inverse, is that continuous? Well, we just got done showing that it's invertible. It's differentiable, right? We just got done showing that this map here is differentiable. So definitely it's continuous. Differentiable maps are continuous. So continuous because differentiable. And what about this one, f prime restricted to u? Is that continuous? Well, f prime is continuous, because that was one of our assumptions at the very beginning, right? That's an assumption in the inverse function theorem, that f is C1. So let me say it this way. It's continuous because we assumed f is C1. So that was way back at the very beginning, up here, f is C1, right? And what about this function? The function that takes the inverse of a linear map. Okay. We actually have not shown that that's a continuous function in this course, but it is a continuous function. I kind of skipped showing it because I didn't foresee where we would need that. Now I'm seeing it. So this is continuous because we are about to prove it. Okay, so therefore, we're going to do that in the next video, actually. Okay, so in the end, therefore, this composite is continuous, and we're finally done. We are finally done proving the inverse function theorem, except for this gap in our course where we have not proven that inv, the taking an inverse of a linear map function, is continuous. So we are done. We have proven the second bullet point here, and so what we have proven is that f restricted to u inverse is a C1 function. That's what these 2 bullet points are saying. So we are finally done proving the inverse function theorem.